Hello everyone, semi-famous Olympic swimmer Schmeichel Phelps here, back to talk to you about similar triangles. Now people are all saying, you look a lot like George Clooney, and I say, well, thank you.
First thing we're talking about is indirect measurement. That's using similar triangles and measurements to find distances that are difficult to measure directly. So some things in real life you can measure with a tape measure, and some things you can't, like a tree or a building. And what you can do is use similar triangles in order to figure out the height of objects that are hard to measure directly with a tape measure or a ruler. When we're talking about indirect measurement, we're talking about using shadows or mirrors in order to create these two similar triangles that we can then use to set up a proportion and solve for that missing height that we're trying to find. Now, the angle-angle similarity postulate says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So we said in previous lessons that two polygons are similar if and only if all pairs of corresponding angles are congruent. Well, how come in this particular instance we only need two pair of corresponding angles to be congruent? Well, it's because in a triangle, if you know that two pairs of corresponding angles are congruent, you know the third pair of corresponding angles have to be congruent as well. So we really only need two to prove that these two triangles are similar. And that's what the angle-angle similarity postulate does. Now, the side-angle-side similarity theorem says if an angle of one triangle is congruent to an angle of a second triangle, and the sides including the angles are proportional, then the triangles are similar. Now, this makes more sense if we look at our example down here. To prove these two triangles similar by the side-angle-side similarity theorem, what we have to do is show that an angle in one triangle is congruent to an angle in another triangle. So angle A is congruent to angle D. We then have to show that the two sides that include the angle in one triangle, meaning the two sides that touch our given angle in one triangle, so segment AB and segment AC, they have to be proportional to the two sides that include our angle in the other triangle, so the two sides that touch our given angle in the second triangle, so segment DE and segment DF. If we know those two sides that include our given angle are proportional, and we know those two angles are congruent, then we know these two triangles must be similar by the side-angle-side similarity theorem. Now, the side-side-side similarity theorem says if the corresponding sides of two triangles are proportional, then the triangles are similar. So this one's a little more straightforward. If you know that all three pairs of corresponding sides in two separate triangles are proportional, meaning they simplify down to the same exact similarity ratio, then you know that these two triangles must be similar by the side-side-side similarity theorem.
Time to dive right into this example.
Now, example 1 says determine if triangle JMN, this small triangle in here, is similar to triangle JKL, this big triangle out here. Well, we're not given any side length measures, and we're not told that anything is proportional to anything else. So it's looking like we're not going to use the side-angle-side similarity theorem or the side-side-side similarity theorem. Instead, it's looking like we're going to have to use the angle-angle similarity postulate. So how do we do that? Well, we need to show that two pairs of corresponding angles are congruent in each of the triangles. Well, we know that each of these triangles, the small right triangle here and the big right triangle, they each have a right angle. So we know that angle J has to be congruent to angle J. So all we have to do is show that another pair of corresponding angles are congruent. Well, if you recall, anytime you see two parallel lines, we should be thinking about the alternate interior angles theorem, the alternate exterior angles theorem, the corresponding angles postulate, which we can use here because if we have two parallel lines cut by our transversal being segment JK, we could say that these two angles, angle JMN and angle JKL, those two angles must be congruent by the corresponding angles postulate. So we could stop right here and say that triangle JMN must be similar to triangle JKL by the angle-angle similarity postulate because angle J is congruent to angle J and angle JMN is congruent to angle JKL. If you want to be an overachiever, you could also see that these two parallel lines were cut by another transversal, segment JL, meaning that these two angles, angle JNM and angle JKL, must be congruent by the corresponding angles postulate as well.
Please don't fail on this. You try like I did in my swimming career.
Okay, doing the same thing here. We're trying to determine if these two triangles are similar. Remember, we have the angle-angle similarity postulate, the side-angle-side similarity theorem, and the side-side-side similarity theorem that can help us do that. So in this particular figure, we see that angle B is congruent to angle Y. So we have an angle congruent to its corresponding angle over here, and we're given the two sides around that angle in each of the triangles, meaning we are given the two sides and the included angle in each triangle. So it's looking like we would have to prove these similar by the side-angle-side similarity theorem. So since we already know that these pair of corresponding angles are congruent, we just have to show that both pairs of corresponding sides that include that given angle in each of the triangles are proportional. So we're going to set up a similarity ratio with both pairs of those corresponding sides, and then we'll simplify each side of that proportion to see if in fact they are proportional to one another. So how do I simplify this? I divide each of these by 4. Over here, divide each of these by 5. And yes, they simplify down to the same similarity ratio, 2 to 1, meaning an angle in one triangle is congruent to an angle in the other, and the sides including the angle in one triangle are proportional to the sides including the angle in the other. So these two triangles then would be similar by the side-angle-side similarity theorem. Now example 2 says determine if the following triangles are similar. So this time we are given all three sides in one triangle and all three sides in another triangle. So it's looking like we're going to have to show that these two triangles are similar by the side-side-side similarity theorem. Well, how does that work? Well, we just have to show that all three pairs of corresponding sides in each of these triangles are proportional. So we're going to set up an extended proportion using all three pairs of corresponding sides. We know that segment NY corresponds to segment PI. We know that segment YC down here corresponds with segment IG down here, and segment CN over here corresponds with segment GP over here. We can then plug in the measure of each of those segments into our extended proportion. We can then simplify each ratio in our extended proportion over here, and we see that they do in fact simplify down to the exact same similarity ratio in each, meaning that all three pairs of corresponding sides in these two triangles are proportional. Therefore, these two triangles must be similar by the side-side-side similarity theorem.
Winning is overrated. Time for you to try.
Okay, doing the same thing here. Again, we are given all three sides in one triangle and all three sides in the other. So to show that they are similar, we're probably going to have to use the side-side-side similarity theorem, meaning we're going to create an extended proportion and show that all three pairs of corresponding sides are proportional. They all simplify down to the same similarity ratio. So I set up my extended proportion where segment FB corresponds with segment NS, segment BI corresponds with segment SA, and segment FI down here corresponds with segment NA down here. We then plug in the measures of each of those segments into our extended proportion over here, and we simplify each of these ratios, and we see that, oh, those do not simplify down to the same ratio, meaning that the three pairs of corresponding sides are not proportional to one another, meaning that these two triangles would not be similar to one another. Now example 3 says given triangle JMN is similar to triangle JKL, we need to find the measure of segment JL. So we are given a small right triangle, triangle JMN, and a big right triangle, triangle JKL. And we are trying to find one of the missing side lengths of our big right triangle, segment JL. So if we know that these two triangles are similar and we're trying to find a missing side length, can't we just set up a proportion like we have been doing and solve for that missing side length? Yeah. So let's go ahead and do that. How do I set up a proportion here? Well, I'm looking for the measure of segment JL. So that clearly has to be in one of our ratios for our proportion. So if we look at our similarity statement, segment JL is going to correspond with segment JN. Remember, the order matters. So on one side of our proportion, we're going to have JN over JL. And that's going to equal, well, over here, we're given the measure of segment JM, so we should probably use that. The measure of segment JM is going to be over the measure of segment JK. So the way I'm going to set this proportion up is the measure of segment JM over the measure of segment JK is equal to the measure of segment JN over the measure of segment JL. Small over big is equal to small over big. Now what I can do is plug in what each of those things are equal to. The measure of segment JM is 8 inches. That goes in here. The measure of segment JK is going to be 8 plus 3.2 inches. That's going to be 11.2 inches. So that goes down here. The measure of segment JN is 5 inches. That goes here. And the measure of segment JL, we don't know that, but we do know that it's going to be 5 inches plus whatever the measure of segment NL is. So we'll just call that part X. So the measure of segment JL we'll refer to as 5 plus x. Now what I can do is I have a proportion, I have a variable, and I can solve for that variable. And how do I solve a proportion? I'm going to use the cross product property. I'm going to multiply across and set the two products equal to one another. Then I can solve for x. So it's going to be 11.2 times 5, and we're going to set that equal to 8 times the quantity 5 plus x. Now remember, when you're multiplying 8 times the quantity 5 plus x, you have to distribute 8 to the 5 and to the x. Now we can solve for x. So I'm going to subtract 40 on both sides, divide both sides by 8, and I get x is equal to 2 inches. But this is not what I was trying to find. I'm trying to find the measure of segment JL. I found the measure of segment NL. So I need to take that x, add it to the 5, and then I will have the measure of segment JL, which is 7 inches. And I'm done.
Tough for you to try.
Okay, this time we are given triangle ACE. The big triangle is similar to triangle ACD, the small triangle. And we need to find x and the measure of segment BC right here. So we know by now that in order to find a missing side length given two similar triangles, we just have to set up a proportion with the corresponding side lengths. And then we can cross multiply, solve for our missing side length. So there's actually two ways to set up this proportion here. You could either set up a proportion based on the corresponding sides of our small triangle and our big triangle. So the measure of segment BC over the measure of segment AC is equal to the measure of segment DC over the measure of segment EC. Or you could also set up a proportion using these two smaller segments down here. Anytime you have a triangle embedded in another triangle like this, and we know that those two triangles are similar, these little tiny segments down here also correspond with one another and simplify down to the same similarity ratio that exists between the corresponding sides. So what I'm going to do in this particular instance, just to show you we can and get the same exact answer, is I'm going to go the measure of segment AB over the measure of segment AC is equal to the measure of segment ED over the measure of segment EC. Now all I have to do is just plug in what each of those segments are equal to over here, and I can solve for x, or the measure of segment AC. So how do I solve for x? I use the cross product property, and I cross multiply, set the two products equal to one another. So I'm going to go 9 times 27 is equal to x times 6. I can then solve for x by dividing 6 on both sides, and I get x is equal to 40.5. Now, is that what we were trying to find? It was part of what we were trying to find. We also need to find the measure of segment BC up here. Well, how do I find the measure of segment BC? There's nothing here. Well, I know that the measure of segment AC is x, or in this case, 40.5, and I know the measure of segment AB is 9. So what I can do is take x and subtract out 9, or take 40.5, subtract 9, and I'm left with the measure of segment BC, which is 31.5 centimeters. Now, example 4 says identify these similar triangles, then find the measure of segment DB and the measure of segment BF. Now, we know that these two triangles are similar because angle C over here corresponds with angle B over here. They have the exact same measures, therefore they are congruent to one another. We also know that segment AF right here is perpendicular to segment CB down here, meaning that both of these angles right here, angle DFB and angle AFC, they are both going to be right angles, meaning they're both going to be 90 degrees. Therefore, they are congruent to one another. So, since two pairs of corresponding angles are congruent between these two triangles, we can say that triangle AFC must be similar to triangle DFB by the angle-angle similarity postulate. Now that I've shown that these two triangles are similar, I can move on to the next part of the question, which is to find the measure of segment DB and the measure of segment BF. Well, you can see in our figure, we are given the measure of segment DB is 5x plus 3, and the measure of segment BF is 7x minus 4. So we need to figure out what x is. So we're going to have to set up an equation to solve for x. Well, anytime you're given similar triangles and you have side lengths for those triangles, you're probably going to have to set up a proportion and solve for the missing side lengths or the given variables. In this case, we are given the measure of segment AC. We are also given the measure of segment DB. We're given the measure of segment CF, and we're given the measure of segment BF. So we need our proportion to include those measures. So we can look at our similarity statement to determine which sides correspond to which sides if you weren't sure. So in setting up our proportion, we know that the measure of segment AC corresponds to the measure of segment DB. We know that the measure of segment CF must correspond to the measure of segment BF. Perfect. Now that we have our proportion, we can plug in what each of those measures are equal to over here, and now we have a proportion that we can solve for x. So how do we solve a proportion like this? We're going to cross multiply. We're going to use the cross product property, which means we're going to cross multiply. We multiply across and set the two products equal to one another so we can solve for x. So remember, when I'm multiplying across like this, 12 times the quantity 5x plus 3, I need to distribute the 12 to the 5x and to the 3. When I'm multiplying 20 times the quantity 7x minus 4, I have to distribute the 20 to the 7x and to the negative 4. I can then solve for x by subtracting 60x on both sides, adding 80 to both sides, and then dividing both sides by 80. I get x is equal to 1.45. But that's not what I was trying to find. I'm trying to find the measure of segment DB and the measure of segment BF. So let's find the measure of segment DB. Remember, the measure of segment DB equals 5x plus 3 meters. So I'm going to take 1.45, plug it in for x here, simplify, and I end up getting that the measure of segment DB is 10.25 meters. I can then do the same thing for the measure of segment BF. I take that x that I found, plug it in for the measure of segment BF, simplify, and I end up getting 6.15 meters. Now example 5 says, given triangle PQR and triangle LMN are right triangles and the measure of segment PR over the measure of segment LN is equal to the measure of segment PQ over the measure of segment LN. We're going to prove that triangle PQR over here is similar to triangle LMN over here. So the first step in a geometric proof is to mark up the figure with the given information. So what are we given? We're given that both of them are right triangles. That's already marked up. Cool. We're also given corresponding side lengths are proportional to one another. So the measure of segment PR corresponds to the measure of segment LN. The measure of segment PQ corresponds to the measure of segment LM. And those two side lengths are proportional to one another. So we now need to move on to step 2 in our geometric proof, which is to state our given as the first step. Done. Step 3 in a geometric proof is to come up with a game plan. How are we going to get from what we're given to what we're trying to prove? Well, this is actually pretty easy. To prove two triangles are similar, we're either going to use the angle-angle similarity postulate, the side-angle-side similarity theorem, or the side-side-side similarity theorem. Here, you can see that we are given two pairs of corresponding sides are proportional, and the included angle is congruent in each of those triangles. Therefore, we could say that these two triangles would be congruent by the side-angle-side similarity theorem. But the only issue is that we don't know that angle P is congruent to angle L. We know that each of these are right triangles. We have to show that each of these angles then must be congruent. So we're going to start by saying angle P or angle RPQ and angle L or angle NLM must be right angles. And that's because these two triangles are right triangles. So it'd just be the definition of right triangles. We can then say because angle RPQ and angle NLM are right angles, that they must be congruent to one another because, if you recall, all right angles are congruent. So we have now shown that the two right angles are congruent to one another, and the two pairs of corresponding sides that include that congruent angle are proportional. That was given. Therefore, these two triangles then must be similar by the side-angle-side similarity theorem. Now, word problem says when Dylan, who is 6 feet 1 inch tall, stands next to a basketball hoop, his shadow is 4 feet 2 inches long, and the basketball hoop shadow is 7 feet 4 inches long. Find the height of the basketball hoop. Round answer to the nearest inch. So let's label our figure down here. Dylan is casting a shadow, as is the basketball hoop. We know Dylan is 6 feet 1 inch tall. We also know his shadow is 4 feet 2 inches long. We know the basketball hoop's shadow is 7 feet 4 inches long. And we want to figure out what's the height of the basketball hoop. So we'll call that x. That's what we're trying to find. So how do I do that? Well, this is where that indirect measurement comes in. The shadows created by two perpendicular objects to the ground create two similar triangles. So what we can do then is set up a proportion between these two similar triangles and solve for our missing height over here. So how do I set up this proportion? Well, I can just go Dylan's height over the height of the basketball hoop is equal to Dylan's shadow length over the length of the basketball hoop shadow. Now all I have to do is cross multiply, solve for x. Oh, how do I multiply these together? Well, I can't have feet and inches in my proportion. So what I'm going to do is convert each of these to inches only. How do I do that? I just multiply the number of feet by 12 and then add however many inches there are. So 6 times 12 plus 1, that is going to be 73 inches. 4 times 12 plus 2, that's going to be 50 inches. 7 times 12 plus 4 is going to be 88 inches. Now that I've converted to inches only, I can actually solve this proportion. So how do I solve this? Well, I need to use the cross product property. I'm going to multiply across and set the two products equal to one another and solve for x. So x times 50, I'm going to set equal to 73 times 88. Now, how do I solve for x here? I'm going to divide both sides by 50, and then I end up getting that x is equal to 128.48 inches. Sweet. Now, this says round to the nearest inch, so you could technically put 128 inches and call it a day, or if you want to do a little A plus work, you could see that all the other measures here are given in feet and inches. So we can convert this to feet and inches. How do we do that? Well, we take the number of inches and we divide it by 12. That'll give us the number of feet. So there are 10.706 repeating feet in the height of this basketball hoop. So we know the basketball hoop is 10 feet tall and then 0.706 of a foot tall. Well, 0.706 of a foot, we just multiply that by 12, and that'll tell us how many inches there are in that much of a foot. So if we multiply these two together, we get approximately 8.48 inches, meaning the height of the basketball hoop is approximately 10 feet 8 inches tall.